Okay, so we have arrived. We've gotten to kind of the big one, the big guns, okay, in terms of statistics here. Okay, hypothesis testing, it's kind of the culmination of everything that we've done in statistics so far, and it's kind of a use, I suppose, of this inferential statistics, an application, if you like. Of where we would see this in the real world, why it's useful, and how we would interpret it. And I suppose the interpretation there can actually be the hardest part for a lot of people, in terms of what we're doing here. So we're going to go through kind of some of the theory. We might even focus on kind of the initial bits and the examples maybe in this video, and then we might leave some questions even for the next one. We'll see how we are time wise. But looking, I suppose, at the start here, a hypothesis test basically is a test to assess whether a stated claim has weight or is significant. We're basically tested some sort of claimed value. Usually it might be that they've given us some sort of parameter, either proportion or mean, and then they've given us a particular value that this parameter might have. And we're testing whether that value seems realistic or fits in with the information, the other information that we have. And how we do that is going to depend on what we're testing. Okay, so that's the first thing to consider. The second thing, or the second term that we'll look at here, is the term significance level. Okay, and usually the letter alpha would be used to represent significance level, and that refers to the probability that the null hypothesis, which is one of our hypotheses that we're testing, is rejected given that it is true. Okay, and what that means basically is that if I'm 95% confident that the true value lies within that range, okay, tying it back to our confidence intervals that we've looked at already, then there's always this 5% chance that it doesn't, or that the value doesn't lie within that range, basically. Okay, so we're 95% sure that it does lie within that range, but that of course means there's a 5% chance that it doesn't lie within that range. So there's a 5% chance that we reject this idea because it doesn't fit the confidence interval that we've set, but there's always a 5% chance that even though it doesn't fit in, it still actually was true. Okay, so that's our significance level there. So again, these are the words we're going to see in these questions here. In terms of doing the confidence intervals or doing the hypothesis tests, I suppose, we have different methods depending on what the proportion or what the parameter we're looking for is. If we are looking for population proportion, we do a confidence interval. Straightforward, cut and dry, that's the only method we've got. If we are looking for mean, we have 3 different ways we could do it. I will say test statistic of all is probably the most popular, okay, and the most straightforward because it is kind of easy to do. Confidence intervals equally, absolutely, okay, work. And I suppose if you're already learning that for proportion, then that's one that you're going to know. And you need to be able to make a confidence interval regardless. The actual doing of the hypothesis test then is just an actual kind of use and interpretation of your confidence interval there. And then p-value is another way that we can kind of test our hypotheses here. I will say for the 3, I've listed 3. You need to know all 3. Okay, it's not a case that you can just learn off one and go, okay, if I have to do it, I'll do this way. You need to know all 3. They could look for a specific one. They could ask you to do one and then do another. P-value, for example, could be requested. Test statistic could be mentioned. Okay, so you need to know how to do all 3. But confidence intervals, I suppose you need to know how to do anyway. Test statistics, you need to know how to do anyway. So I suppose the only new one to learn here is just the p-value. And again, there's not an awful lot to it. So I suppose for hypothesis tests, we've particular steps we're going to follow here. So I've laid them out below. The first step we're going to take with all of these is to state the hypotheses. Okay, we start with what we call the null hypothesis, which is our H0 or HO. This is basically the default assumption, the claim in the question. It's a claim that there's no effect, no change, no relationship. It has stayed the same. It is what they say, what's been said, anything like that. Basically, we have to have a value for the null hypothesis. Okay, so in terms of the questions here, your null hypothesis is always going to be p is equal to or mu is equal to. The alternative hypothesis is the opposite conclusion, is the alternative case. If that's not the case, it's the other side of the coin, and that's just going to be essentially that it's not equal to whatever the particular value is that we have. Okay, what we're trying to do here, okay, in a kind of simple terms, is we're nearly testing this null hypothesis. Okay, we're kind of testing whether if this null hypothesis is true, does everything else fit in as well? Okay, does everything else seem yet reasonable and likely under that assumption? Okay, and because we're testing that, we have to have a value. Okay, we can't really test that it's not something. So we can test that it is equal to something and see whether that assumption kind of works with everything else. It's kind of like contradiction, really, kind of similar to our proof by contradiction. We're kind of taking that assumption, running with it, and then seeing, does that assumption still work with all the other evidence that we have and information that we have here? So first step is always state the two hypotheses must be done. Okay, a lot of the questions will lead you through these steps as well, but there's no guarantee. Step 2 will be to choose which test you're going to do and conduct that test. We will either do a confidence interval, which, as we've said, is the only method for p for proportion. Test statistic would come from mean. P-value would also come from mean. We will then make a decision based on the test results. We decide whether we will reject or fail to reject the null hypothesis. Okay, how we come to that conclusion is going to depend largely on the method of testing that we're using. Okay, and we'll look at kind of how that can be decided and interpreted then, and then we write a conclusion based on our decision there. Okay, your conclusion generally should kind of incorporate maybe your decision there as well, and also should tie back to the original question. I've given a sample here. We might say, based on the hypothesis test at the 5% level of significance, you might change that for 95% confidence. Doesn't matter once you get that point across. Important to include that reference, I think, to 95% confidence. I think that's worth including. We reject or fail to reject the null hypothesis. So that idea of just saying, well, what was the decision? What was the end result? We might then say that if we're rejecting it, that there's sufficient evidence to suggest that the mean has changed, that the proportion is not equal to what it was. If we fail to reject, we might say there's not enough evidence to say that. What you should notice there is that we're not saying we accept the null hypothesis. Okay, going back to what I said at the start, the null hypothesis is kind of an assumption, a claim in the question that maybe a value has stayed the same or that it has changed or whatever. We're testing at 95% confidence. Just because we can't prove it's wrong doesn't mean it's true. Okay, is I suppose the best way I can describe that. So just because we can't mathematically prove that it is false doesn't mean we immediately go, well, I couldn't disprove it, so it's true then. Okay, so think about, I suppose, like an example would be if you were, I suppose, you've gone home and you, I don't know, so you've lost something. You're on the bus home, and you think that you might have left your phone in school. Okay, you're not sure where your phone is. You might have left it in school. You're on the bus home. You're not sure. You check at home. Okay, you check at home to see is it at home, and you don't find it at home. So it probably is at school then. But it could have fallen out along the way. It might have fallen out on the walk home. It could be on the bus somewhere. So just because you tested at home and found that it wasn't at home doesn't mean it is at school. I suppose is kind of a very simplistic way of kind of looking at it. I say giving a complicated example, but that's the kind of idea there. Just because we can't disprove it, doesn't mean it's true. Okay, just because we can't show that it is false doesn't mean that it is true. Okay, there's always still a chance that it's still false. So we're going to get into the methods of testing then. The first method of testing is a 95% confidence interval, and we've looked at these, or I've looked at these already in separate videos there for both proportion and mean, but just as a summary here of the two methods, for proportion and for mean, the same idea. We put the parameter in the middle, whether it's proportion or population proportion, population mean, and then on either side we take the sample proportion and add and subtract the standard error to that, okay, including our 1.96 as well to account for the 95% confidence, because we're basically saying we want a value that is 1.96 standard deviations away from that sample, that kind of population mean or population proportion or whatever it is. If the statistic we have, if the claim we have is outside the interval, then we reject the null hypothesis. We're basically saying we are 95% confident that the true value is within this range. So if the claim is not within this range, then we are 95% confident that we can reject the null hypothesis, that it's false. Okay, again, as we said at the start, there's always that 5% chance that we reject it and it was actually true. but we're 95% confident that we can reject it here. If the value they've claimed is within the interval, we fail to reject because there is a possibility that they are right, that it is that value. There's always a chance that's not as well, okay? Just because it's within that range doesn't mean that it is that value. Okay, so say our confidence interval is between 20 and 40. If they claim it's 35, it could be 35. It could equally be 27. Okay, so just because their value is within the range, it means we can't outright say that it's rejected, but we fail to reject. We don't accept that that is the actual answer either, because there's still that margin of error and everything involved there. Okay, I've put that note as well that this is the main test for population proportion. Okay, so if it's to do with proportions, so you're thinking about percentages or fractions of a group, then you're going to be looking at a hypothesis test following this layout here. Okay, so we're going to look at two examples with confidence intervals. We're going to look at one for each, for proportion and for mean here. So a company launches a marketing campaign for a product. Before the campaign, 30% of customers bought the product. After the campaign, a random sample of 400 customers were taken. It was found 140 customers purchased the product. Carry out a hypothesis test to see if the percentage of customers buying the product has changed. Okay, so we are testing whether the percentage of customers has changed. Our first step always is to state the hypotheses. So my null hypothesis is always that it hasn't changed. Okay, I know this question is to do with proportions because it's to do with numbers of people, not averages. There's no mention of means, so therefore it must be proportions. So we are basically saying that P, my null hypothesis is that P is 0.3, that it hasn't changed, and it's still 30%. Okay, so it's still 30% of customers who've bought the product. The alternative hypothesis then is that it has changed and is no longer 0.3. Okay, a common mistake here would be to say that it's 0.7, but the opposite of being 0.3 is not being 0.3. Okay, it's not 0.7. Just because it's not 0.3, it could be 0.31, 0.32, it could be 0.4. Okay, it can be any other number, it's just not 0.3. Okay, so be careful with that one. So is and is not. We need to look at all of our information now. P hat is the sample proportion. So that's the 140 customers out of the 400 customers. So let's work out what that proportion gives me in total here. That's 0.35. So my sample proportion was 0.35. My sample is 400 people. We could also look at maybe our standard error here, which is the P1 minus P over N. Okay, and knowing as well that we use our sample proportion here because, as we've been saying, P is very rarely known in these questions here. And even though in this case we're testing whether it's 0.3, it's only a test. Okay, it's only a test. We don't know whether that is what it is. Okay, so we're testing what it is, so we're not going to use that then as part of the test here. So let's just work out what this value is, just to save us a little bit of working out when we come to the next part. Over 400, and that is 0.0238. So let's set up our confidence interval now. So our confidence interval for the population proportion is P hat plus my error and P hat minus my error. Okay, so that's 0.35 plus 1.96 times the standard error. And minus 1.96 on this side. So we're basically saying here that on average, the population proportions are about 0.0238 from the actual proportion there, and we want to look at how far is 1.96 standard deviations away from the actual value here. So looking at my confidence interval then, 0.35 plus 1.96 times 0.0238 is 0.3966. And subtracting for the other side of the interval as well gives me 0.3035. So we are basically saying that we think the true value for P is between 0.3035 and 0.3966. Okay, So this is step 1. This is going to be step 2, our test. Step 3 is to make a decision. As 0.3 is outside the interval, okay, so we can kind of see that there, 0.3 is not included in this range of values. We are then going to reject that claim or that hypothesis. We reject the null hypothesis. So because it's fallen outside the interval, because we are 95% confident that 0.3 is not the population mean there, because it doesn't fall within our range that we've set up, then we can reject that claim that it's still 0.3. So our conclusion then, we might say, based on the test at 5% level of significance, there is sufficient evidence, so there's enough evidence here, to reject the null hypothesis, H0. The mean, not the mean, excuse me, the proportion of customers buying the product has changed from 30%. Okay, so the idea here is that it's no longer 30% anymore. So we've set up this interval, we've set up this range within which we think the actual value lies, and 30% doesn't fall within that range. So we think it actually has changed. If we look at the confidence interval, the range within which we think it is above 30 up as far as 40. So if anything, we could even maybe infer here that it probably has increased, okay, because the 0.3 is actually below that confidence interval. So if we want to go further, we might in fact say that the confidence interval has increased, which suggests that the population proportion is actually larger than the 0.3 or higher than it was originally. So we might say that this campaign has possibly been successful here because it has led, presumably, to an increase then in the proportion of customers buying the product. So there's actually quite a bit that we can kind of infer from our hypothesis test here. Let's look at the same sort of question then applying to population mean and see, can we spot the differences straight away? First of all, I suppose the biggest giveaway that it's mean is reference to average. Okay, really that's kind of going to be the thing. Reference to average, reference to mean, that's going to give away that it's a sample mean question. So the average weight is 100 grams with a standard deviation of 4 grams. We're selecting 25 bars and we find the sample mean weight to be 98 and standard deviation of 4. So still the same standard deviation. Test whether there's evidence to support the company's claim. So let's go with our null and alternative hypothesis here. So we know the null hypothesis is usually that the population mean is equal to something. The standard deviation is that it is not. The company claims the average weight is 100, so my claim here is that it is 100. The alternative is that it's not 100. Okay, fairly straightforward, kind of cut and dry here is our hypothesis. Our test here is whether it is 100 or not. Okay, second step is to conduct a test and decide what we're doing. We're going to do confidence interval here since that's kind of what we're sticking with. So we'll lay out all the information that we have. Okay, so we want to test confidence interval. We need X bar, which is sample mean, which is 98. We need standard deviation, which is 4. And we need sample size, which is 25. Okay, my confidence interval for the mean is 1.96 times sigma over root n, where sigma over root n is the standard error of the sample means. Okay, so essentially the standard deviation for those sample means, we want them to be within 1.96 standard deviations, okay, of the actual value there. So let's fill in the values that we can. We can fill in X bar of 98. We can fill in 1.96 times 4 over root 25. And the same here, minus 1.96 times, 4 over 25. Sorry, I meant brackets there and I did a square root. And X bar, of course, 98. So let's work out this value then. 98 plus 1.96 times 4 over root. Trying to get rid of my square here. There we go. 4 over root 25 is 99 point. Let me see now, have I filled in something incorrectly here? Yeah, 25 bars. Okay, so that's going to give me 99.568, and on the other side we'll subtract that and get 96.432. Okay, so looking at our values here, we're looking between 96.432 and 99.568. Okay, so because it's very, very close here, it's very, very close here, but because we're allowing some decimals, okay, we're going to reject the null hypothesis. So as 100 falls outside the confidence interval, we reject the null hypothesis. Okay, so as it falls outside the confidence interval there, we're going to reject our null hypothesis. Okay, so that's kind of our decision. And then 4 is there is sufficient evidence to suggest the mean weight is not 100. Now, from what we can see from our confidence interval is it's very, very close. It's very, very close. If anything, it's too small. Okay, if anything, it's actually too small. It's below the 100 there, which is kind of the problem. So it's actually too small, or smaller than they have claimed. Okay, so we're getting the idea of them here, hopefully. So we're going to keep moving on a little bit because I want to look at the other type of test that we can do, and then we'll do an example of that type as well. And this is only for population mean. Okay, so only for population mean, we have that example of test statistic here. And a test statistic, okay, we've looked at this already in the population mean section, but it's basically a z-score, okay, or a z version of for the sample means. It's a measure of how many standard deviations is a particular sample mean from the true population mean. Okay, so how many standard deviations is a certain x bar from an actual value of mu? We are allowing 1.96 standard deviations. That's the most we will allow. Okay, that's the most we will allow. If it's any more than that, then it falls within what we call the critical region, and we would say that it is statistically significant. What we're basically saying there that is, if my test statistic is more than 1.96, or indeed less than minus 1.96, so falls within either of those regions, either side, then it is so far from the population mean value that it probably isn't a fluke. Okay? Like if I do a test of a sample and the result I get is like 4 standard deviations away from the mean, okay, or my assumed mean, because remember we're testing an assumption here. If the value I get ends up being like 4 standard deviations away from the assumed mean, then it's unlikely that that assumed mean is correct. It's basically the view that we're taking here. Okay, based off one sample. Okay, it's possible you get a fluke, it's always possible you get a fluke, but we have allowed ourselves a fair range there up to 1.96. So getting a value, and I suppose the further away it is, the more kind of sure nearly we can be of rejection. But basically that's the idea. So a z-score, as we've always said with z-scores, it's a measure of how many standard deviations is a value away from the mean. In terms of a test statistic, it's how far is this, in terms of kind of standard errors, how far is this sample mean from the population mean. We are allowing up to 1.96. Any more than that, and that kind of suggests, right, this probably isn't just down to kind of chance, this is probably actually a significant value, and therefore might mean that this mean value we're working with isn't actually true. Okay, because it doesn't, the rest of this information doesn't fit in with it. Okay, Ignoring the theory part of it and just focusing on practically how would we do it, we would calculate the test statistic using our formula, which again is in our formula and tables book, but it is the one written here. And if the absolute value is larger than 1.96, so that's kind of allowing us for either positive or negative 1.96 there. If that's larger than that, we reject the null hypothesis. It's too far away, it's unlikely to be down to chance, it's probably actually a significant value there. Okay, so calculating it, again, you can go back to kind of the population mean video there to kind of look at it, or we'll be into some of the examples here anywhere where you can see it there. But looking then at the last type of test, which is very closely related to that, a p-value is basically the probability that is associated with that test statistic. So based on what I've said already, if I have kind of a standard or normal distribution here, and we have say 1.96 here, which is kind of what we're saying we're allowing up to 1.96. And let's say I do a test statistic and I get 3. Okay, let's say I get a value of 3 here. What we're basically saying here is 3, this value I've gotten for x bar, this sample mean that I've gotten, is 3 standard deviations away from the true population mean mu. Okay, we're basically saying it's 3 standard deviations away from this true population mean of mu. Okay, a p-value is the probability that somebody is here. So the probability that this x bar, or I suppose z really, is greater than 3. So we're basically saying, what is the probability that if I pick a sample, it'll be bigger than this particular sample that I've gotten here? So we're saying maybe for this one case that I've gotten right, okay, it was 3 standard deviations away. What's the probability that this would have happened under this assumption? Okay, what's the probability of this happening? If that probability is really low, then again, we say that's unlikely to be down to chance. Okay, now in calculating p-values, we also consider the alternative side here as well, the -3, and look at the probability here. We call it a two-tailed hypothesis test. Okay, bearing in mind that both of these would have equal areas there, are covering equal because of the symmetry of the curve. They cover equal areas, so the probabilities would be the same. Okay. So looking at the writing here, I suppose to kind of talk through that again, a p-value basically is the probability of getting this value or a more extreme value under this assumption of the null hypothesis, or if the null hypothesis is true. So if we do a test and get a really, really small p-value, then that suggests that this was very unlikely to be down to chance. So let's say we do a test and the probability that I would have gotten this value is like 1%. Then there was only a 1% chance that I would have gotten this value under this null hypothesis. And that really does suggest that the null hypothesis is unlikely to be true then. Okay, because it's very unlikely I would get this random fluke of a value under this overall assumption. If I assume that the average should be 50 and then I get a value of like 70, and the probability of me getting that value was like 1%, then it's very unlikely that the mean is actually 50. Okay, it's a good test of whether we can change it or not. Basically, we want a small p-value. We want the probability that we get this value to be very, very small, because that means we can reject the null hypothesis. And really here, rejection is the only thing we can kind of be certain of, because the other side is we fail to reject and we're not as sure on that one. We can always reject and we outright reject then. We want a low p-value. A low p-value means a strong evidence against the null hypothesis. Okay, and again, as I said, it's the probability that I would get this value if the null hypothesis was true. So your Z test here is maybe the number of standard deviations from the mean. So it's more of a test of how far from the true value is this parameter that, or this sample value that I've gotten. The p-value then is the probability that I would get that value or a more extreme value. So let's look at that in an example. A coffee shop claims that the average time customers spend in their shop is 45 minutes. That's a claim for population mean. A researcher believes the claim may not be accurate. To test this, they randomly sample 36 customers, find the average time spent is 41 minutes, and a standard deviation of 9. Okay, so you can kind of see as I'm going there, I'm just filling in different points as I go there. Okay, so let's fill in some of these values now into our hypothesis test for the first step here. So hypothesis test, first step is always list your hypotheses. First step is that we list a value for the mean, which was 45, excuse me, not 41. And the alternative, of course, is that it is not 45. Okay, so the average time spent is 45. You can elaborate if you want here as well. Average time spent is 45 minutes. Okay, let's go next. This time we're going to try with a z-test, so I'm going to need to use my formula here, which is x bar minus mu over sigma over root n. Let's fill in all of these values. My sample mean was 41. My actual mean that I'm testing is 45. Sigma was 4. And no, it was not. It was 9. And it's over 36 here. 9 over root 36. So let's see. So minus 4 over 9 over 6. And that's going to give me what? 2.67. Okay, so let's have a look at that. So 41. Okay, grand. So 41 minus 2.67. Minus 2.67. So we are looking for the probability that we get a value of minus 2, or no, we don't, sorry, excuse me, I'm not looking for that yet. I'm just looking at my z-score. So the test here is if my test statistic, the absolute value is greater than 1.96, we reject the null hypothesis. So let's try that out. Absolute value of minus 2.67 is just 2.67, which is greater than 1.96. So we do, in fact, reject the null hypothesis. And what we're basically saying there is this value is just too far from that suggested average value. Okay, it's just too far from that suggested average value. It's too far below average for us to accept that null hypothesis. So we'll reject the null hypothesis here. Okay, so that kind of comes into basically our decision making here. And our last step is just to kind of conclude. So there is sufficient evidence to reject the coffee shop's, it was a coffee shop, wasn't it? Yeah, to reject the coffee shop's claim. And based on our sample, because our sample was below, it was kind of less than, or with standard deviations below the mean there, we might even say that in reality it's probably actually lower than the true value. The true value is actually probably on the lower end there. So continuing on to the second part of the question, then part B was to calculate the p-value and interpret that. So the p-value, okay, and I kind of glossed over actually the calculation of that here, but it's 2 times the probability that Z is greater than the absolute value of the test statistic, okay, and the absolute value coming from the fact here that we've already said those two areas are the same, and it's just easier to work with the positive version is kind of the gist of it there. So 2 times the probability that Z is greater than the absolute value of Z test. Okay, and kind of if we want to do a little sketch here to consider this, minus 2.67 plus 2.67 here, and we're looking in these sections here then. So let's find this out. The probability that Z is greater than 2.67 is equal to 1 minus the probability that Z is less than 2.67. Okay, again, that's just from our general working with z-scores there in this case. Okay, and that's going to be 0.9962, which gives me 0.0038. So my p-value here is 2 times 0.0038, which is 0.0076. which is 0.76%. So basically what we're saying here is if the null hypothesis is true, there is a 0.76% chance of getting this value, or a more extreme sample mean. Okay, or in another way of phrasing it there would be maybe to say that if the null hypothesis is true, we would expect to get this value 0.76% of the time. So the fact that we have gotten it does suggest something's a bit out of the ordinary here. So because of that, we would reject the null hypothesis as 0.0076 is less than 0.05. That 5% chance, we're only willing to accept a 5% chance there, or the 5% level of significance, and because it's so much lower than that, we're going to reject the sample, the null hypothesis there in that case. There's a very, very small chance that this value could be down to chance, or could be down to just being a fluke here, because it's such a low probability of it happening. So we reject the null hypothesis. Okay, so two different methods there, both really depending on the question, okay, depending on what you have. Whether you decide to use test statistic or test statistic or confidence interval for a population mean, largely up to you. They can request a particular one. You need to know how to do a confidence interval regardless, but they can request a specific one. If they don't, test statistic is probably quicker. You can kind of see there it's quite kind of short and sweet there really, but just because it's quicker doesn't mean it's the best one to do. P-value again they could look for, and often that might be how they look for it, is as an extra part to the question they might look for the p-value. But besides that, then yeah, it's just a case of kind of following through the question. And really with the hypothesis tests, the main things as well is following those steps of naming your hypotheses, and then following or understanding that interpretation at the end as well.